Hi there, this is James, and today I want you to get ready to experience a supercharged metabolism and a thrilling ride with Graves' disease using some various unique medical mnemonic. So buckle up and let's start with a medical mnemonic for the clinical features of Graves' disease. Now, before we discuss the pathology of Graves' disease, let's describe some basic physiology. What I have here is a thyroid follicular cell that is extremely important in the synthesis of thyroid hormones. Adjacent to the colloid, the yellow part, is the apical membrane. On the opposite side, we have the basolateral membrane, which is adjacent to the vascular compartment. Now, the thyroid gland wants to synthesize thyroid hormones, and the signal will come from a thyroid releasing hormone in the hypothalamus that will also signal the TSH, which is the thyroid stimulating hormone. So, TSH will bind to TSH receptors on the thyroid membrane. This would lead to a cascade of events that we're about to describe. So, for the thyroid gland to be able to synthesize the thyroid hormones, it needs one, iodine and thyroglobulin. Thankfully, the follicular cells are able to synthesize the thyroglobulin themselves, which is a great thing. Now we need the iodine to get into the colloid so that that synthesis will take place. But the iodine doesn't get into the follicular cell as easy as we think because we have the iodine in the form of iodide, which is a charged element. And it is very difficult for the iodide to move across the membrane. So there is a gate here which is called the sodium iodide symporter. And so through a secondary active transport, sodiums are able to get iodide into the follicular cells here. Now it's important because that is the way iodide gets into the follicular cells. In the follicular cells, the iodide that we have, which is charged, is then converted into iodine by a thyroperoxidase enzyme, and that's an oxidative process. This gate here is called pendrin, and through the pendrin that's on the apical membrane, the iodine is able to move into the colloids. On the other side, whilst thyroglobulin is synthesized, it is also put into the colloids through exocytosis. So what I have here is thyroglobulin. And as you can note, thyroglobulin has these tyrosine residues on them. Okay, so this is where the iodination process must take place. In other words, iodine must bind to these tyrosine residues. So we have the thyroglobulin meet the iodine, and we call that iodination. So the iodine that comes in may bind to one of the tyrosine, and that is going to be called MIT, monoiodotyrosine. If we have two of the iodine binding to the tyrosine, we're going to call it DIT, which is diiodotyrosine. Now it is important because if you have two of the DITs coming together, we're going to call it T4. And if you have one MIT plus DIT, that is going to form T3. All right, so let me write that here. For example, if we have a DIT plus a DIT, we get T4. Okay, if we have, say, a DIT plus an MIT, we get T3. So I'm here to explain that. So once that is formed and the organification, that means the incorporation of the iodine into the thyroglobulin is done, and it can be put back into the follicular cells depending on the signals coming from the pituitary gland when we need the hormones. So in this follicular cell here, I have one DIT, okay, that binds to another DIT, and so we get a T4. And I have one DIT that binds to an MIT, so we get a T3. And it's also packed into vesicles, and they can then be diffused across the membrane into the vessel or into the vascular compartment where they bind to thyroid binding globulins. These are the major carriers that transport thyroid hormones. There are other minor ones such as transthyretin and albumins, but mostly it is thyroid binding globulins that carries these thyroid hormones. It's important to note that T3 is the most potent or the most active thyroid hormone, and T4 is the most abundant hormone. All right, so from here, the thyroid hormones may be sent to their target organs, and its effect will then take place. So, in Graves' disease, there is the production of TSH-receptor antibodies from the activated B cells. These antibodies are able to disguise themselves as the TSH, so they are able to signal through the cells to synthesize hormones by activating the TSH receptors. So Graves' disease is an autoimmune disease. With the production of these antibodies, it's able to cause enormous secretion of thyroid hormones that causes quite some unwanted symptoms. Now let's take a look at the effect of the thyroid hormones on its target cell. Once the hormones are produced, and with the help of the TSH signals, these hormones are transported into their target cells. So what I have here is T4 or thyroxine, which is the most abundant, and here it is bound to thyroid binding globulin. T4 finds itself in the target cell. Inside this target cell, that is the cytosol, there is an enzyme called monodeiodinase. As the name implies, mono, which means one, and deiodinase is to remove. So there is the need to remove one iodine from the T4 and convert the T4 into the active T3 hormones, a process which is known as peripheral deiodination. And this, in fact, accounts for about 85% of the total T3 levels in the body. Now, that process would lead to T3 being available to bind to the thyroid hormone receptor, and with the help of another transcription factor called retinoid X receptor, there is transcription, and then the mRNA is made and translation of proteins. It's important to remember that the monodeiodinase enzyme may be grouped into types. Type 1 is often found in skeletal muscles as well as the liver, and type 2 found in neurons, and type 3 in the placenta. Now let's take a look at peripheral deiodination, a process in which monodeiodinase removes one iodine from T4 and converts it into the active T3. What you see here is T4, and you're certainly correct, because we have one iodine and a second iodine, and we have a DIT, diiodothyronine, and we have a similar one on top, and we can also call that DIT. So if you have two DITs put together, you get a T4, all right? And we need the body to convert the T4 peripherally into an active T3 or into T3. So we need T4 to be converted. And so there is something I need you to take note of. Now on this T4, there are two rings. What I have here is the inner ring, and what I have here is the outer ring. Okay, now when the removal of the iodine occurs on the outer ring here, if let's say one of these iodine is removed, then that is going to produce the active T3 that we need. But on the other hand, if the deiodination or the removal of the iodine occurs in the inner ring here, for example, as in this case, then we're going to form a reverse T3, which is often elevated in the euthyroid syndrome. Thank you for watching, and if you find the content useful, then subscribe to the channel. Bye.